settle in and let your breathing slow until the ceiling above you feels like a private night sky. The room is still, the air is soft, and far beyond it all, the stars pretend to be steady. They are not. They drift, they tremble, they quietly react to things you cannot see. Tonight, you are going to listen the way astronomers listen, not for fireworks, not for drama, but for the smallest changes in starlight, a faint wobble that repeats, a tiny dip that returns like a refrain. And somewhere in that gentle pattern, the first planet found around a sun-like star, 51 Pegasi b, waits patiently to be noticed. The sleepless scientist will keep the lights low and the universe honest. You think the night sky is a painting, fixed, polite, and flat, but it is more like a crowded room of strangers, each one shifting weight, clearing a throat, tapping a foot. The movements are small, but they add up, and the light carries gossip. If you stare at a bright star long enough, it feels loyal. Same place, same sparkle, same ancient calm. But a star is a furnace wrapped in a gravity well. It is always rearranging itself, always ringing with tiny vibrations, always tugged by whatever happens to be nearby. And near a star, the most interesting things are often the ones you cannot see. Worlds that do not shine, worlds that do not announce themselves, worlds that simply pull. That is the quiet human urge, isn't it? To look at a familiar kind of star, something like our sun, and wonder if it has company. Not because the universe owes you neighbors, it does not, but because your mind keeps drawing the same simple picture. A light, a few dark stones circling it, maybe one with oceans, maybe one with weather, maybe one with a creature staring back. Astronomy does not begin with answers. It begins with patience and with noticing insults to the pattern. A star that should be still but is not. A brightness that should be constant but dips. A spectrum that should sit neatly in place but slides just a little and slides back. Big discoveries tend to arrive like that, not as explosions. More like dust you wipe off a shelf and suddenly realize it was never just dust. So you keep your eyes on the familiar stars. You let them lull you with their steadiness, and then you learn how to detect the ways they lie. And once you are listening for tiny changes in the dark, you are ready to hear the oldest trick starlight can play on you, because a planet does not merely orbit a star. That is the children's drawing. That is the simplified diagram that fits in the corner of a textbook page. In reality, the star is not the unmoving center. The star is a dancer, too heavy, yes, and arrogant, yes, but still dragged into the choreography. You have two bodies, a star and a planet, and they both feel gravity. They both pull. They both orbit a shared balance point called the center of mass. It is a tidy phrase for something deeply unromantic, the spot where the universe does its accounting. If the planet is small, the center of mass sits deep inside the star. The star only does a tiny shuffle, a polite wobble, like someone pretending they did not hear the music start. If the planet is large, the star's wobble is bigger, still not dramatic, still not visible to your bare eyes from across space, but it is there and it repeats. That repetition is everything. Noise is random. Weather is random. Your instruments are moody. Your hopes are extremely moody. But a planet is faithful in the most indifferent way. It returns. It tugs again. It makes the star lean toward you and away from you on a schedule. So how do you see a wobble you cannot see? You do it the way you notice an ambulance on a distant street. Not by the shape of it, but by the sound-changing pitch as it comes closer, then moves away. Light can do a similar trick. When a star moves toward you, its light shifts very slightly toward the blue end of the spectrum. When it moves away, it shifts toward the red. This is the Doppler effect, the same idea as the siren, but carried by photons instead of air. And yes, I know, you are lying there thinking, that sounds almost reasonable, until you remember the scale. Stars are far. The wobble is tiny. The shift in light is so slight that it feels like trying to measure a heartbeat by watching a lighthouse. Congratulations, you have just met the core problem of exoplanet discovery. The universe is generous with wonders, but stingy with evidence. So astronomers became accountants of starlight. They learned to split a star's light into a rainbow, a spectrum, and measure where certain dark lines fall. Those lines come from atoms in the star's atmosphere absorbing specific colors. They sit at very particular wavelengths, like barcodes. When the star wobbles, the barcode slides. Not enough to notice in a casual glance. Enough to notice if you measure it the same way, night after night, with the same careful obsession. This is radial velocity, though you do not need the name to feel the mood of it. It is a method made of repetition. It is a method made of refusing to be distracted. You watch the star. You record the spectrum. You compare it to the night before. You do it again and again and again. The data does not arrive like a proclamation. It arrives like a whisper you have to confirm is real, and not your own mind trying to entertain itself. And the dance is slow enough and the wobble small enough that early astronomers spent decades getting almost there. They found hints. They found embarrassment. Because a star can mimic a planet in cruel little ways. Star spots can rotate in and out of view, changing the light. The star's surface can boil and churn. Magnetic activity can add jitter. Even Earth's atmosphere can smear and shift things at the worst time, like a foggy window you cannot clean. So you do not just need a wobble. You need a wobble with the right rhythm, the right smoothness, the right repeating grace. And you need to be certain you did not manufacture it with your own tools, which is why the discovery you are here for, the first planet around a sun-like star, did not come from a single genius having a single perfect night. It came from a lot of nights that looked boring, and a few people who could tolerate that boredom better than most. And if you can imagine a star's quiet wobble, you can imagine the long, careful nights it takes to prove it is not just your instruments dreaming. Picture the observatory as the opposite of a rocket launch. No fire, no cheering crowds, no dramatic countdown. Instead, a dome that opens with a slow, practical groan. Cool air sliding in, dry and thin, smelling faintly of dust and metal. The telescope moves like something half asleep, heavy and deliberate, as if it resents being asked to turn its head. Inside, there is routine, not the glamorous kind. the kind that keeps you alive. You calibrate the instrument. You take a reference spectrum from a lamp, something with known lines, so you can tell if the machine has drifted. You correct for temperature changes that make metal expand and contract, because physics does not care about your schedule. You correct for Earth's own motion, because while you are trying to measure a star's wobble, you are also riding a planet that spins and orbits like it has somewhere to be. Then you take the exposure, a star's light, collected and guided, fed into a spectrograph like a thin stream into a measuring cup. You wait. You collect enough photons to make the barcode clear, and then you do it again tomorrow. The romance of astronomy is mostly marketing. The reality is closer to quality control. A good observing run is a string of quiet successes. The dome opens, the weather holds, the tracking stays smooth, the data looks clean. A bad observing run is every tiny failure, stacked. Thin clouds you cannot quite see, wind that shakes the telescope by a fraction, which is all it takes. A component that warms slightly, shifting the spectrum. A computer that decides tonight is the night it wants attention. Astronomers learn to mistrust beauty. A clean signal is suspicious. A perfect curve is suspicious. Your brain loves patterns too much. So they cross-check. They observe the same star with different instruments. They compare notes across teams. They look for the same period, the same repeating cycle, the same amplitude. They ask the cruel question over and over, is this a planet, or is this just a star being a star? And sometimes, a team finds something that refuses to go away. A wobble that remains after you correct for the obvious mistakes. A rhythm that survives the instrument's quirks. A signal that shows up again like a soft tapping at the door. Patient and unbothered by your skepticism. This is how discovery actually feels. Not like victory, more like slowly realizing you are not alone in the room. And eventually, after enough quiet nights, one particular star starts to behave like it is keeping a secret. The star is called 51 Pegasi. It sits in the constellation Pegasus, which is an ancient way of saying, we drew a horse on the sky, and now you have to live with it. To your eyes, it is just a point of light. To a telescope, it is a sun-like star, not identical, but familiar in temperature and mass. The kind of star you might expect to host planets, if planets are not some rare cosmic mistake. And in the mid-1990s, two astronomers, Michel Mayor and Didier Queloz, were watching it with a spectrograph designed for precision. They were looking for exactly the kind of wobble we have been whispering about. What they found was not what the polite theories predicted. Before this moment, the leading expectation was comforting and conservative. If other planetary systems existed, they might look roughly like ours. Rocky worlds close in, gas giants far out. Long, leisurely orbits, decades of patience needed to see a full cycle. That expectation was not unreasonable. It was also wrong. Because 51 Pegasi was wobbling with a period of about 4 days. 4 days, not 4 years. Not 12 years like Jupiter, 4 days like a frantic little world sprinting around its star as if chased. At first, that should sound like an error. It should sound like a glitch in the instrument, or a star spot, or some subtle trick of the data reduction. It should sound like the universe making a fool of you, but the wobble repeated, night after night, the same rhythm, the same smooth curve, and the size of the wobble implied something heavy, not a small rocky planet, something closer to Jupiter in mass. So now you have a problem. The fun kind, the kind that ruins your assumptions. A Jupiter-like planet should not be that close to its star. In our solar system, a planet like Jupiter lives out beyond the frost line, where ices can condense and big cores can form. Close to the sun, it is too hot, too sparse, too chaotic for a gas giant to build itself easily. And yet, there it was. Or rather, there it was not, because nobody saw it directly. They saw the star being tugged around like a larger dog on a leash, forced to pace in a tight circle. This planet became known as 51 Pegasi b. The letter is a little piece of quiet bureaucracy, the first planet around that star to be found. So it gets the first letter, the universe's wonders, filed alphabetically. It was a hot Jupiter, a gas giant, skimming close to its star, so close that its year is shorter than your work week, so close that its atmosphere would be blasted by stellar radiation, so close that the very idea of a Jupiter there feels like finding a whale in a bathtub. The surprise was not just that it existed. The surprise was how easy it was to confirm once you knew what you were looking at. A 4-day period means you do not have to wait years to see repetition. You get multiple cycles in a month, multiple chances to test the pattern, to see if it holds. In a way, the universe handed astronomers a gift, a strange gift wrapped in scalding heat, because the short, steady signal acted like a lullaby with an insistent refrain. It returned before doubt could grow too large. It allowed confirmation. It allowed other teams to check the claim and see the same wobble in the same star. And once that happened, the field changed overnight, not in mood, because astronomers are not built for overnight emotions, but in possibility. If a hot Jupiter exists, then planetary systems are not obligated to be like ours. If migration is possible, if gas giants can move inward after forming, then the architecture of solar systems can be messy, creative, indifferent. It also meant something else, something quietly radical. Planets around sun-like stars were not philosophical. They were physical. They could be detected. They could be cataloged. They could be studied with the same cold methods used for everything else. And that meant the sky was no longer just a ceiling of lights. It was a census waiting to happen. And when one unexpected planet shows up, it quietly changes how you look at every other star in the sky. Because now every steady-looking star becomes suspicious. Every calm point of light might be hosting a fast, hot giant, or a packed family of smaller worlds, or a lonely planet circling in the dark. The comforting model of our solar system, but elsewhere, begins to melt. Not into chaos, into variety. You start to realize that normal is a story you tell yourself when you have only one example. With 2 examples, the universe becomes a little less obedient. Soon after 51 Pegasi b, other hot Jupiters showed up, not because they were the most common kind of planet, necessarily, but because they were the easiest to detect with the tools of the time. A big planet tugs harder. A close-in orbit repeats quickly. So the early catalog of exoplanets was biased toward these loud, fast, correct answers. That bias is not a flaw. Exactly. It is a reminder. You do not discover reality all at once. You discover what your instruments can hear, and the instruments of the 90s were ears tuned to heavy footsteps on a short hallway. The quiet padding of an Earth-like planet that was still beyond the threshold, still drowned in noise. But even within those limits, the diversity began to show. Some systems had multiple planets packed closer than Mercury, like beads crowded on a string. Some had planets on eccentric orbits, stretched into long ovals, diving in close then fleeing far away, like they could not decide where they belonged. Some had massive planets far out, the more traditional arrangement, and the mix of patterns made it clear that nature does not build one blueprint. The universe is creative not because it wants to impress you, but because physics has many ways to be stable. And there is something oddly comforting about that. Not the kind of comfort that tells you everything is fine. The kind that tells you your expectations are not the boss here. It also forces humility into the process of science. Astronomers had to accept that they were wrong about what to expect. They had to rewrite formation theories to include migration, disk interactions, gravitational scattering, the quiet violence of young systems rearranging themselves. And while they did that, they kept watching because theory follows observation the way a shadow follows a body. But the most soothing part of this story is the pace. There is no rush in the sky. A planet does not care if you are tired. It will tug its star on schedule, which means you can, in your own soft way, become an observer too. Not by building a spectrograph in your bedroom, please do not, but by adopting the attitude, the patient suspicion, the willingness to be wrong, the ability to find meaning in small repeats. And speaking of how we find these worlds, sometimes you do not watch a star wobble, you watch it blink. Because there is another method, quieter in concept, but powerful in results. Instead of listening for the star's movement, you watch for a small shadow. Imagine a porch light on a summer night. Now imagine a tiny moth crossing in front of it. The light dims just a little and then returns. If a planet's orbit is lined up just right, it can pass directly between you and its star. That is a transit. From far away, you do not see the planet as a disk. You see the star get slightly less bright for a while, then recover. The dip is small. For a Jupiter-sized planet, it might be around 1%, give or take. For an Earth-sized planet, it can be closer to a whisper, a few parts in 10,000. A change so subtle your eyes would never notice. But detectors do not get bored. Detectors do not blink. The beauty of transits is the repetition. A single dip could be a fluke. 2 dips at the same spacing is a hint. 3 dips is a pattern you can start to trust. From the timing between dips, you get the planet's orbital period, its year. From the depth of the dip, you get the planet's size relative to the star. A deeper dip means a larger planet. A shallower dip means a smaller one. And if you have radial velocity data as well, you can combine them. Radial velocity gives you a mass estimate. Transit gives you a size estimate. Mass and size together give you density. And density is the first crude clue to what a world might be made of. Rock, gas, something in between, like a mini Neptune with a thick atmosphere and a hidden core. This is where exoplanets stop being mere tugs and become, in a gentle way, objects. But there is a price. Most systems are not aligned for transits from our viewpoint. The geometry has to be lucky. It is like needing a coin to flip and land balanced on its edge. Not impossible, just rare. So to find many transiting planets, you do not watch one star. You watch thousands, hundreds of thousands. You stare at a dense field and wait for the repeated blinking. That is how the method grew from a clever idea into an industrial process. Not loud, not dramatic, just relentless observation. And this is where the story begins to feel like the universe is letting you read its mail. A planet passes in front of its star, and the starlight carries the news across space. Your telescope catches it, your software marks it, your tired human brain eventually accepts it. Still, for this first pass tonight, keep the feeling simple. A star that dims, then brightens, then dims again. A steady heartbeat in light. It is counting gentle shadows, spaced by patient time. And once you start believing in these small, reliable shadows, you can begin to imagine what these planets might be like without ever seeing them at all. Because most exoplanets will never be photographed as neat little globes, not with our current tools, not in the crisp way your mind wants. They are too close to their stars, too drowned in glare, too far away. So you learn to accept indirect knowledge. You learn to become comfortable with inference. It is like hearing footsteps in another room. You do not see the person, but you know their weight, their pace, the pattern of their movement. You can tell if they are pacing nervously or walking calmly. You can even guess if they are carrying something heavy. Exoplanet science lives in that same neighboring room. A close-in planet with a short period is likely hot. Not warm beach day hot, more like oven left on, door locked hot. A far-out planet with a long period is likely cold. Cold enough for exotic ices, for methane to behave like water, for atmospheres to collapse and freeze onto the surface. A big planet blocks more light in transit. A massive planet tugs its star harder in radial velocity. When you put these together, you start sorting worlds into rough families. Hot Jupiters, bloated and scalded. Warm Neptunes, wrapped in thick gas. Super Earths, a term that sounds heroic but mostly means bigger than Earth, which is not necessarily a lifestyle improvement. Sub-Neptunes, common and strange, worlds with no solar system counterpart. And sometimes, when conditions are right, you can do something even more delicate. During a transit, a small amount of starlight passes through the planet's atmosphere before reaching you. If the planet has an atmosphere, that air can absorb certain wavelengths, leaving faint fingerprints in the spectrum. It is subtle. It is hard. It is full of caveats, but it can hint at water vapor, sodium, methane, carbon dioxide, CO2, and other molecules that tell you what the air might contain. You are not smelling the air directly. You are tasting it through a straw from light years away. And the result is not a perfect portrait. It is more like a sketch seen through fog. But even a sketch is enough to make your mind wander. You begin to picture skies with unfamiliar colors because different molecules scatter light differently. You picture clouds not of water, but of silicates or metal vapors or sulfur compounds. You picture winds driven by tidal locking, where one side of the planet always faces the star, stuck in eternal day, while the other side freezes in endless night. Some hot Jupiters may have rain made of glass, blown sideways. Some may have temperatures that strip atoms and leave tails like comets. Some may be slowly evaporating, their atmospheres leaking into space like a sigh. Congratulations, you have discovered that planet is not a promise of comfort. It is just a category for something heavy enough to be round and selfish enough to hold itself together. But remember the tone here. This is not about fear. It is about scale and about the gentle honesty of physics. The universe makes worlds the way a river makes stones, by endless repetition, by pressure, by time, by indifference. And you, lying safe in the dark, get to learn about them without paying the travel costs. A very good arrangement. All things considered, for now, let the details stay faint and far away. Let them be careful hints, not full images, because this whole field grew from learning to love hints. It began with a wobble that repeated, a star that leaned, then leaned back, a pattern that refused to be dismissed. And in a moment, we will return to those long, patient nights and the people and machines that kept watch until the pattern became undeniable. Until 50, one Pegasi bee stopped being a rumor and became a measurement. So, you put yourself back in that control room mood, the one with stale coffee, quiet keyboards, and the soft tyranny of precision. You are not chasing a bright dot through an eyepiece like it is the 19th century. You are feeding photons into a device that behaves like a very picky accountant. A spectrograph does not care that you are tired. It only cares where the lines fall. Those dark absorption lines in a star's spectrum, they are not decoration. They are atoms and ions in the star's outer layers, stealing specific colors. Hydrogen takes its favorite bites. Sodium takes its own. Iron, calcium, and a whole crowd of others do the same. Each one leaves a thin, neat scar in the rainbow. You learn the scars well enough to recognize them even when they drift, and on the nights you are lucky, the drift is smooth. But smooth is never enough. Smooth is what you get when your instrument warms up slightly. Smooth is what you get when your calibration lamp is having a quiet identity crisis. Smooth is what you get when your data reduction pipeline quietly decides to round a number. So you become careful in a way that is almost spiritual. You calibrate before and after. You track the temperature inside the spectrograph housing because metal expands like a slow sigh. You stabilize the optics, or you try to, because light is unforgiving about tiny misalignments. You also correct for Earth, because Earth refuses to sit still for your experiment. You are riding a rotating globe, which means you are sometimes moving toward the star, sometimes away. Then the whole planet is orbiting the sun, adding another seasonal push and pull. You subtract those motions because you are not here to measure yourself. You are here to measure the star's tiny, reluctant shuffle. The word for this, if you want the tidy label, is barycentric correction. It means you are translating your measurements into the frame of the solar system's center of mass. Human translation. You are trying to stop your own planet from smearing the evidence. And when you finally look at the data, the wobble you want is not a picture. It is a curve on a plot. A gentle wave, a rise toward blue, a slide toward red, and back again. A heartbeat that belongs to a star that does not know you exist. If you are unlucky, the curve is messy. It has extra bumps. It has jitter. It has that irritating quality of being explainable in 3 different ways. One of those ways is a planet. The other 2 are usually the star itself or you. Stars are not calm. They only look calm from far away. A sun-like star has convection, hot material rising, cooler material sinking, like a pot that never stops simmering. It has oscillations, sound waves trapped inside it, making the surface gently throb. It has magnetic fields that twist and snap and create dark star spots, cooler regions that rotate in and out of view, and all of that can make spectral lines shift and distort. So, the first exoplanet hunters learned to treat every promising signal like a suspicious text message at 2 in the morning. It might be real. It might be a trap. It might be your own wishful thinking wearing a disguise. This is why confirmation matters. Not the dramatic kind, not headlines. The boring kind. You check the same star with a different instrument. You check it on different nights, under different weather. You look for the same period, the same phase, the same amplitude. You ask another team to try because nothing cures pride like independent replication. In the case of 51 Pegasi, the signal was stubborn. It kept returning on that 4-day rhythm. It did not smear away when you corrected for Earth's motion. It did not vanish when you looked for correlations with stellar activity indicators. Activity indicators are little side channels of doubt. You measure, for example, how certain calcium lines behave, because magnetic activity in the star's atmosphere can brighten those lines. If your radial velocity signal matches the star's activity cycle, you start to suspect you are seeing a moody star, not a planet. But if the activity stays quiet, while the wobble stays rhythmic, your suspicion shifts. So the claim hardened, not into certainty, because science rarely allows that luxury, into something more useful, a model that made predictions. A 4-day planet should produce a 4-day wobble. It should do so consistently. It should not care about your feelings, and it should be possible, in principle, to find other signs. Now, you may want the satisfying moment where someone points a telescope and sees the planet, a clean little disk, a proud discovery photo. That is not how this story goes. The first era of exoplanets was mostly invisible worlds, proven by their effects. You had mass estimates, usually written as a minimum mass, because radial velocity only measures the motion along your line of sight. If the orbit is tilted, you see less of the wobble and the true mass is larger than your estimate. The math for that tilt includes a sine term, which is why you sometimes hear the phrase m sine I. Human translation: you are missing an angle and the universe will not tell you. So, for 51 Pegasi b, you got a minimum mass around half of Jupiter's, enough to be a gas giant, enough to be embarrassing for tidy formation theories. And because it orbits so close, it lives in a region where tides are brutal. Tides are not just an ocean thing. Tides are what gravity does when it is stronger on one side of you than the other. On a close-in planet, the star's gravity stretches it. Over time, that stretching tends to lock the planet's rotation, so the same side always faces the star. One hemisphere stuck under permanent daylight, the other condemned to endless night. If you imagine standing on such a world, you do not. You never stand on such a world. You are a bag of water and salts, and this is not a vacation destination. But you can imagine the physics anyway, because physics is free. The day side bakes under constant starlight. The night side tries to radiate heat away into space. Between them, winds roar, trying to even out the temperature difference. The atmosphere becomes a conveyor belt of hot gas and shocked chemistry. And there is another quiet insult. The star's radiation, especially in ultraviolet, can puff up the planet's upper atmosphere. Hydrogen can be heated until it escapes, leaking into space. Some hot Jupiters may be slowly evaporating, their edges being shaved off by light. Congratulations, you have found a planet that is being cooked and peeled at the same time. And yet, from the standpoint of discovery, it was a gift. A big planet close to its star is loud in radial velocity. It yanks the star around more than a small planet would. It repeats quickly, making the pattern easier to verify. So what did the rest of astronomy do with this gift? It copied it, not the planet. The method, teams refined their spectrographs. They hunted for more short-period giants. They built instruments with better stability, better calibration, smaller systematic errors. One of the quiet revolutions was calibration itself. To measure tiny Doppler shifts, you need a wavelength ruler that does not bend. Some early methods used absorption cells, like iodine gas placed in a light path, imprinting its own forest of lines onto the spectrum. Those iodine lines served as a reference grid. Later, new tools appeared: thorium-argon lamps, etalons, and eventually laser frequency combs, which are as close as humans have come to making a perfect optical ruler. A frequency comb gives you evenly spaced lines at known wavelengths. Human translation? You stop guessing where the ticks on the tape measure are. As the rulers improved, the wobble threshold dropped from tens of meters per second to a few, to around 1. And 1 meter per second is the speed of a brisk walk, measured in starlight. From light years away, you are lying in bed, and a scientist on a mountaintop is measuring a star's motion with the delicacy of watching someone's breath fog a window. It is absurd, and it works. But even as radial velocity improved, another method began to take over the census, because watching a star blink is more scalable than watching it wobble. A single spectrograph can only take so many stars per night, but a camera can stare at a field of thousands and never look away. This is where you drift into the world of transit surveys. You stop being the lone observer at a telescope. You become a pixel in a dataset. Imagine yourself as a detector element on a camera, a small square of silicon, cooled, quiet, dutiful. Photons hit you, and you count them. You do not care what they mean. You only count. Night after night, you count the same star's photons. Most nights, the count is steady within the noise. A little jitter from atmosphere, a little variation from instrument, a little randomness, because photons arrive like rain, not like a metronome. And then, one night, the count dips, not dramatic, a slight thinning, like someone briefly turned the porch light down by a tiny notch. If you are a human watching the raw data, you might miss it. Your attention drifts. You blink. You decide to make tea, but the software does not blink. It runs a matched filter across the light curve, searching for box-shaped dips that repeat. It folds the data over trial periods, stacking cycles on top of each other until a faint pattern becomes a clear dent. It is patient in a way humans cannot afford to be. And when the dip repeats on schedule, you begin to believe. A transit gives you the planet's radius relative to the star. But the star's radius must be known, and stars like to complicate that too. So you learn about stellar characterization, because exoplanet science is always secretly star science. You estimate the star's temperature from its spectrum and colors. You infer its radius from models, sometimes aided by parallax measurements, which tell you the distance. If you know how bright it appears and how far away it is, you can infer its true luminosity. From luminosity and temperature, you can estimate radius. Human translation: to know the planet, you must first know the light bulb. Transit depth is essentially the area ratio, planet disk over star disk. So a Jupiter-sized planet crossing a Sun-sized star makes a dip of about 1%. An Earth-sized planet makes a dip closer to 100 parts per million. A whisper. Transit duration tells you about the orbit's geometry and speed. The time between transits gives the orbital period, and from that period, using Kepler's third law, you can estimate the orbital distance. Again, assuming you know the star's mass. Kepler's third law is one of those old pieces of physics that refuses to die. Period squared proportional to distance cubed. Human translation: the farther out you are, the slower you move, and the universe keeps track of it with neat bookkeeping. So, with a transit, you can guess temperature too, in a rough way. Closer orbit means more stellar flux. But albedo matters, and atmosphere matters, and heat redistribution matters. And you usually do not know those. So you settle for the equilibrium temperature estimate, a polite lie that assumes the planet is a simple sphere, absorbing and re-emitting energy evenly. Real planets do not behave that way. Real planets have weather and chemistry and circulation. But even a polite lie can guide you. And this is how exoplanets went from rare trophies to catalogs. The sky became a spreadsheet. At first, the catalog was full of big close-in planets, because those are easiest to see. Then, as missions improved, smaller planets began to fill the list. Worlds with sizes between Earth and Neptune, which our own solar system never bothered to include. Those worlds are among the most common in the galaxy, as far as we can tell. And they are still strange, because we have no local example to visit and poke. Some may be rocky with thick atmospheres. Some may be water-rich with deep oceans and high-pressure ice beneath. Some may be gas-shrouded mini-Neptunes with small solid cores hidden under a lot of hydrogen and helium. You want a simple classification because humans love sorting. The universe does not always cooperate. Now, there is a trap here, a dangerous little mental shortcut. You see a planet in the so-called habitable zone, and your brain starts decorating it. Blue oceans, green continents, clouds, a quiet sense of being not alone. But the habitable zone is only a statement about distance and starlight. It is the region where, with the right atmosphere, liquid water could exist on the surface. Could, not will, not must. A planet can be in that zone and be a frozen ball. If it has little greenhouse gas, it can be in that zone and be a runaway greenhouse if it has too much. It can be in that zone and have no surface at all if it is a small Neptune with a deep atmosphere over crushing pressures. So, you learn to enjoy the restraint of the evidence. It keeps you honest. It keeps you from turning every dot into a story with a happy ending. But sometimes, the evidence gives you more than a dot. During transit, a tiny fraction of starlight passes through the limb of the planet's atmosphere. If molecules are present, they absorb at specific wavelengths, so the transit depth becomes slightly deeper at those wavelengths, because the atmosphere is effectively larger where it absorbs. This is transmission spectroscopy, a fancy term for something intimate. You are reading the planet's air by watching a star dim in different colors. If the atmosphere is clear and puffy, features can be strong. If the atmosphere is heavy, with high mean molecular weight, features are muted. If the planet has clouds or hazes, they can flatten the spectrum, hiding the fingerprints. Clouds do that on Earth too. The universe loves consistency. And because these signals are tiny, you often need space telescopes. The atmosphere of Earth is not just a nuisance, it is a spectrum of its own. Water vapor, oxygen, carbon dioxide, all imprint features that can confuse your measurement. So for detailed atmospheric work, you prefer to get above it, above the turbulence, above the absorption, above the weather. This is where your mind drifts toward those quiet machines in orbit. They do not sleep. They do not get cold. They do not have to argue with wind. But before we go up there, linger a little longer on the human part of this, because it is easy to imagine astronomy as pure serenity, a clean discipline, people in quiet domes, listening to the universe hum. It is calmer than many jobs, yes, but it is also full of failure that is not dramatic enough to be interesting. A night can be lost to thin cirrus clouds that you only notice in the data later. A guiding error can smear a spectrum just enough to ruin precision. A detector can develop a new bad pixel cluster, like a rash. A cable can fail silently, and your clock stamps become wrong. And the cruelest part is that a false signal can look very real. It can repeat for a while, then drift away when you fix one small systematic. It can appear in one instrument and not another. It can be the ghost of a data pipeline. So, the culture of exoplanet detection became cautious. A claim is not just a claim. It is a set of checks. For transits, you worry about eclipsing binaries. Two stars orbiting each other can mimic a planet transit if the light is blended. A faint background binary lined up by chance behind your target can create a dip. A grazing stellar eclipse can look like a shallow planet if you are not careful. So, you do follow up. You take spectra to measure radial velocity and rule out stellar mass companions. You do high-resolution imaging to check for nearby contaminating stars. You compare transit depths in different filters, because a true planet blocks the same fraction regardless of color. Mostly, a star eclipse can change with color. You become a detective of boring details, and slowly, from these details, the galaxy fills with confirmed worlds. Not because the universe suddenly became kinder, because humans learned to listen with better discipline. Now let your mind widen again, not in a dramatic way, just gently. Once you know that planets exist around sun like stars, the question changes. It stops being, are there other worlds? It becomes, how many and what kinds? And the answer, so far, is mildly humiliating for anyone who thought our solar system was the template. There are systems where multiple planets orbit closer than Mercury, all with years of a few days to a few weeks. There are systems with super-Earths, which means bigger than Earth, but not necessarily friendlier. There are systems with resonant chains, planets locked in gravitational rhythms, like gears that cannot slip. Resonance is when orbital periods form simple ratios, 2:1, 3:2, 4:3. When one planet goes around twice for every one orbit of another, their tugs repeat in a consistent pattern. This can stabilize or destabilize depending on the configuration. It is cosmic peer pressure, bodies forcing each other into regularity until something breaks. Our own solar system has hints of this. Jupiter's moons Io, Europa, and Ganymede are in a resonance called the Laplace resonance. They tug each other in a way that keeps their orbits slightly eccentric. That eccentricity drives tides. Tides drive heat. Heat drives geology. So resonance is not just a mathematical curiosity. It is a way to keep a moon warm enough for hidden oceans. It is a way to turn gravity into an engine. In exoplanet systems, resonances can tell you about formation and migration. If planets formed farther out and moved inward through the protoplanetary disk, they could be captured into resonant chains. Later, disturbances can break the chain, leaving near resonances and scattered architectures. Migration is the polite word for a messy process. A young planet interacts with the gas and dust disk around the star. Gravity creates spiral waves in the disk. Those waves exchange angular momentum with the planet. The planet moves inward or outward depending on conditions. Type 1 migration for smaller planets. Type 2 for giants that open gaps. Human translation: the disk is a conveyor belt that can drag planets away from where they were born. So, that hot Jupiter that bothered everyone, it likely formed farther out, then moved inward. It did not grow in place like a delicate houseplant. It was relocated by gravity and gas, then parked close to the star, where it now sizzles. Some hot Jupiters may have moved even closer and been consumed. A star can eat planets. It is not a metaphor. When a planet is close enough, tides can transfer angular momentum and cause the orbit to decay. The planet spirals inward over long time. Eventually, it crosses a point where it cannot hold itself together. It can be shredded, forming a debris disk, and then accreted. You will not be around to watch it, but you can know it happens because the physics does not ask permission. And there is another kind of variety, one that is quieter. Free-floating planets. Some worlds may be ejected from their systems entirely, flung out during early gravitational chaos. No star, no day, just a cold wandering sphere moving through the galaxy. You detect these sometimes through microlensing, which is another method of noticing the universe's small betrayals. Gravitational microlensing happens when a foreground star passes almost exactly in front of a background star. The foreground star's gravity bends the background star's light, magnifying it for a short time. If the foreground star has a planet, the planet can add a brief extra blip in the magnification. It is a one-time event, no repeat, a fleeting alignment, a cosmic coincidence. And that is why microlensing finds planets in a different way. It is not a method of patient repetition. It is a method of waiting for luck in a crowded field, but it can find planets far from their stars and even rogue planets, because it does not care about the planet's own light. It cares about its gravity. Gravity is not subtle when alignment is perfect. So, your catalog of methods grows. Radial velocity, transits, microlensing, direct imaging, in rare cases, when young, massive planets glow in infrared and can be separated from the star's glare with careful optics. Astrometry, measuring the star's position on the sky as it wobbles, a method that becomes powerful with space missions like Gaia. Each method has biases. Each method hears different instruments in the cosmic orchestra, and when you combine them, you get a less wrong picture. What does that picture look like? It looks like planets are common. It looks like small planets are extremely common. It looks like systems are diverse, with architectures shaped by disk physics, migration, resonances, and violent scattering. It looks like the universe does not mind wasting material on worlds that will never host anything that appreciates them, which brings you, gently, to a thought that is both comforting and inconvenient. If worlds are common, then Earth is not the default. Earth is an outcome. You are not sitting at the center of the story. You are sitting on one stage among many, in an endless theater where most seats are empty. And still, you care. You care even when the evidence is faint. Because the act of finding another world is like finding another version of the question, not are we special, but what kinds of normal exist? Now, keep that thought soft. Do not turn it into a crisis. You are not required to solve meaning tonight. You can just notice what exoplanets do to your sense of place. They make the sky feel less like decoration and more like geography. A long time ago, the stars were fixed points used for navigation. Then they became suns. Now they are suns with systems, and you are lying in a room, in a small pool of warmth, while your species quietly builds a map of things it cannot visit. It is a very human kind of absurdity, a gentle refusal to stay ignorant. Now, speaking of refusal, there is a stubborn limit that has hovered over this whole story. The limit is noise. Noise from the star. Noise from your atmosphere. Noise from your instrument. Noise from the simple fact that photons arrive with randomness. To find smaller planets, you need either extreme precision or extreme numbers. You can improve precision with better spectrographs and better calibration. You can improve numbers by watching huge samples of stars continuously. And that second approach is where space surveys come in, like quiet factories in orbit. But before you leave the ground entirely, it helps to understand why space is such a tempting place to do this work. On Earth, you have air. Air is life. Air is also turbulence. Turbulence makes starlight shimmer. It blurs the point spread function, smearing your star image over more pixels. It introduces time-varying noise. You can correct some of it with adaptive optics in certain cases, but not for everything. Air also absorbs. Water vapor absorbs. Oxygen absorbs. Carbon dioxide absorbs. If you are trying to measure tiny changes in starlight, Earth's own breath gets in the way. And then you have day. The rude interruption of sunlight. A ground telescope cannot stare at one field continuously for months without losing it to the planet's rotation. Space telescopes can. So you begin to appreciate the appeal of a machine that just watches. No clouds, no sunrise, no wind shaking the dome. Just a cold camera taking data the way a glacier takes time, steadily and without emotion. Space surveys do not feel romantic. They feel administrative. A mission like Kepler, for example, stared at a single patch of sky for years, watching over 100,000 stars. It looked for tiny dips, repeating. It did not move much. It did not chase novelty, it just collected. And this changed exoplanet science in a way that is almost unfair. With Kepler, the detection of transiting planets became statistical. You could measure occurrence rates. How common are Earth-sized planets close to Sun, like stars? How common are super-Earths? How common are planets in the habitable zone? You could correct for geometry, because you know most planets will not transit, so you can estimate the true population from the ones you do see. It is census work, not treasure hunting. The result is a galaxy that seems crowded with planets. More planets than stars, likely? Some stars with none, some with many. And even though Kepler did not look at bright nearby stars, it gave you something valuable, a sense of how ordinary planets are. Then, missions like TESS, the Transiting Exoplanet Survey Satellite, shifted focus. Instead of staring at one field, it scanned large portions of the sky, focusing on nearby bright stars. Those are easier to follow up with radial velocity and atmospheric studies. You see how the field evolves. First, you prove planets exist. Then, you count them. Then, you choose the ones you can actually study in detail. And all of this work is built on quiet repetition. Light curves, spectra, catalogs, pipelines that chew through nights of data and produce candidate lists for humans to scrutinize. It is not a heroic narrative. It is closer to bookkeeping. And yet, in that bookkeeping, you sometimes find worlds that feel like they belong in fiction. Planets so close to their stars, they are being torn apart, leaving dust tails. Planets orbiting two stars, with sunsets that are genuinely complicated. Planets with densities so high they might be iron-rich remnants. Stripped cores of former giants. Planets so low density they are puffballs, like cotton candy held together by gravity's mild insistence. And still, the most important part is not the weirdness. It is the implication that weirdness is normal. Your solar system is one roll of the dice. It produced a neat architecture that made it easy for 19th century textbooks. Other systems did not get the memo. Now let that drift into something closer to home. Why do you care? Not why astronomers care in grand proposals. Why you, specifically, care enough to listen to this in the dark. Because exoplanets do something subtle to your sense of loneliness. Not by promising you company, by reframing what loneliness means. If there are countless worlds, then isolation is not rare. It is the default. Most planets are dead rocks. Most are gas spheres with no surface. Most are too hot, too cold, too irradiated, too young, too old, too chaotic. The universe is not empty of worlds. It is empty of comfort. And yet, it keeps making places anyway. That is the strange generosity of physics. Not kindness, just productivity. You can find that thought either bleak or soothing, depending on what you need. Because if nothing is designed for you, then you are not failing when the universe feels indifferent. It is simply behaving as advertised. You are a biological accident with a calendar and a mortgage, living on a wet rock that has been lucky for a suspiciously long time. And when you look outward and find other rocks and other gases and other orbits, you are not finding a cosmic family. You are finding context. Earth becomes less like the center of reality and more like a particular solution, a particular combination of mass, distance, chemistry, and time. A planet that kept its water, a planet with plate tectonics, a planet with a magnetic field that helps deflect solar wind, a planet with a large moon stabilizing its tilt, perhaps, a planet with a history of impacts that were terrible, but not too terrible. You do not have to cling to any of these as destiny. You can just note them as conditions. And then you can note something else, the quiet fact that you are learning this from a safe place. You are not the astronaut with a cracked visor. You are not the probe melting on Venus. You are not the hot Jupiter being sandblasted by light. You are a listener, a creature warm enough to dream, thinking about places that do not care. That is the soft detour, the reason this topic matters without demanding urgency. And since you are already drifting among far-off suns, you may as well drift toward the machines that keep watch while the rest of the world sleeps. The ones that do not need clear skies because they live above the weather, and the ones on the ground that learn to behave, finally, like precision instruments instead of hopeful toys. Above the weather, the night is not really a night at all. It is a steady, refrigerated kind of day. You are a telescope now, not the romantic kind with brass tubes and eyelashes at an eyepiece. You are a box of mirrors and baffles and solar panels, drifting where gravity is gentle but never absent. Your skin feels sunlight on one side and the cold bite of space on the other. The temperature swings want to twist you, to warp you, to make your measurements sloppy. So you are built like a stubborn thought, insulated, regulated, constantly correcting yourself. Down below, continents rotate in and out of darkness. Cloud systems spool and unravel like slow white bruises. City lights glitter in clusters and then vanish under the curve of the earth. It is all very pretty and also completely irrelevant to your job. Your job is to stare, not to glance, not to admire. To stare at the same stars with the same tired devotion for months and years. Because a transit is a small theft of light, and small thefts are easiest to catch when you never stop watching the door. On the ground, an observatory fights wind and weather and daylight. Up here, you fight different enemies, reaction wheels that jitter, cosmic rays that punch your detector, tiny drifts that smear pixels. Space is not quiet. Space is just quiet about the things humans evolved to notice. A cosmic ray hits your camera sensor, and you get a bright little slash in the data. Not a planet, just a particle from some ancient explosion, arriving late like an unpaid bill. You flag it, you clean it, you keep staring, and you are not alone up here in the dark. There are the older machines, like Hubble, which was built for many things and then recruited into exoplanets, like a veteran pulled back into service. There are the survey machines, built specifically to count dips and stack statistics. There are the newer machines, like the James Webb Space Telescope, which is less a telescope and more a cold, delicate ear for infrared whispers. They all share a trait that is very unromantic. They do not get to be surprised. A space mission is planned to death. Targets selected, observing windows scheduled, data pipelines prepared, failure modes anticipated. Even the thrill, if it arrives, comes in a spreadsheet. So imagine yourself as one of these missions and feel the calm, administrative grind of it. You point at a patch of sky and you hold. Your camera measures brightness again and again. Every star becomes a time series, a long line of numbers that looks like boredom until something repeats. And then you hand it down to Earth, because you are not the one who decides what it means. You are the one who collects. You are a net in the cosmic ocean, catching whatever swims through your field. Down on the ground, the humans do the part they tell stories about. They build pipelines that flatten the light curves, removing instrumental trends. They correct for thermal changes in the spacecraft, because even metal in orbit has moods. They correct for pointing drift, because pixels are not perfect little buckets. They have quirks. They identify systematics that affect many stars at once, because those are usually not planets. This is the funny thing about modern exoplanets. You do not just need a telescope. You need a philosophy of error. You need to know how your instrument lies. You need to know how the star lies. You need to know how you lie to yourself when you want a result. So, the pipelines search for what are called threshold crossing events. Human translation, a dip that is deep enough and consistent enough to bother with. Most dips are garbage. Some are eclipsing binary stars. Some are instrumental glitches. Some are background blends. Some are real planets, quietly doing what planets do. And the reason this works at all is repetition. A transit is a ritual. The planet comes back, steals light again, and leaves. It does this without apology, without variation, unless something else is tugging it. That tugging, by the way, becomes its own kind of story. If you have multiple planets, their gravities disturb each other. That means the timing of their transits can shift slightly. One transit arrives a little early, another a little late. These are transit timing variations. They're small, sometimes minutes, sometimes less, but they are real and they are useful. Because transit timing variations can reveal additional planets you cannot see directly. They can estimate masses. They can map resonances. It is like hearing two people walk down a hallway and noticing their footsteps fall out of sync. You do not see them, but you learn their relationship. And sometimes you get a system that feels like it was built to show off. TRAPPIST-1, a tiny red dwarf star with a packed set of planets, some near resonance. Kepler-11, a tight cluster of worlds with thin spacing. Systems where the planets are so close that if you stood on one, the others would look bigger than our moon. You think that should be rare. But the universe seems to like crowded neighborhoods. It also seems to like humble stars. Red dwarfs are smaller and cooler than the sun. They are the most common stars in the galaxy, and they live a very long time. They are efficient and stingy with light. From a detection standpoint, they are convenient. A small star makes a planet's transit deeper because the planet blocks a larger fraction of the disk. A small star also wobbles more for a given planet mass, making radial velocity signals larger. So if you want to find Earth-sized planets, you often end up looking at stars that do not look like the sun. Not because you want to, because physics is practical. But red dwarfs have their own personality problems. They flare. They spit ultraviolet and X-rays. Young red dwarfs especially can be violent little lamps. That radiation can erode atmospheres, strip volatile molecules, and make habitability complicated. So you trade detectability for comfort, and the universe laughs quietly. And yet, the surveys keep going. Kepler taught you that planets are common. TESS brings you closer, giving you brighter stars that allow follow-up. Ground-based surveys fill in the gaps, especially for larger transits that are easier to see through Earth's atmosphere. Then comes the slow, careful second act, characterization. A detection is a name in a catalog. Characterization is where you try to turn it into a place, even if only vaguely. You follow up a transiting planet with radial velocity to measure its mass. If you have mass and radius, you get density. If density is high, you suspect rock and metal. If density is low, you suspect thick atmosphere, hydrogen-rich envelope, or even a puffy heated state. But density is still a blunt tool. A planet could have a rocky core and a thick atmosphere and still land in the same density bin as something with more water. A planet could be iron-rich, like a stripped core, and be dense enough to feel like an exaggeration of Mercury. A planet could be porous or inflated by heat and be underdense, like a balloon. So you want more. You want to know what the atmosphere is made of, if there is one. You want to know if there are clouds, hazes, photochemical smog. You want to know if the planet has an ocean, or just a supercritical fluid layer, or nothing resembling a surface at all. And this is where the space telescopes become less like surveyors and more like forensic analysts. During a transit, starlight filters through the atmosphere at the planet's limb. During a secondary eclipse, when the planet passes behind the star, you can measure the combined light minus the planet's contribution. That gives you thermal emission and reflected light, if you are lucky and the signal is strong. Hot Jupiters were the first targets for this because they are large and hot and loud in infrared. They practically advertise themselves. You measure phase curves, watching the system brighten and dim over the orbit as different parts of the planet rotate into view. From that, you infer heat transport. You infer winds. You infer whether the hottest spot is shifted eastward, blown by atmospheric jets. You never see the weather. You infer it from light, like reading a person's mood from the way they shut a door. This is an odd intimacy. A planet dozens of light years away, and you are learning the distribution of its heat. And then, occasionally, you try the hardest trick: direct imaging. This is not a method for most planets. Stars are too bright. Planets are too close. The contrast is brutal. Trying to see an exoplanet next to its star is like trying to spot a firefly next to a stadium floodlight from across an ocean, while someone shakes your binoculars. So direct imaging needs special techniques. Coronagraphs, which block the star's light inside the telescope. Star shades, in future concepts, which would fly as separate spacecraft to cast a precise shadow. Adaptive optics on the ground, correcting atmospheric turbulence in real time, turning a blurry star into a tighter point. Even then, direct imaging usually finds young, massive planets far from their stars. Young planets are still hot from formation, still glowing in infrared. Far planets are more separated in the sky, easier to resolve. You end up with images that are not colorful postcards. They are faint dots near a brighter dot, circled in a paper-like evidence in a case file. But a dot is still something. And when you take a spectrum of that dot, you can learn about molecules like methane and water vapor. You can estimate temperature and gravity. you can start to see that planets are not just numbers, they have chemistry. Speaking of chemistry, it is the most patient villain in this entire story, because chemistry can mimic life. Chemistry can erase life's signatures. Chemistry can make a planet look promising and be deadly, or look dead and be interesting. So when you hear people talk about biosignatures, you should picture a cautious scientist with a headache. Oxygen in an atmosphere could be produced by photosynthesis. It could also be produced by water loss and photodissociation, followed by hydrogen escape, leaving oxygen behind. Methane could be biological. It could also come from geology, from serpentinization reactions in the crust. CO2 is common and not especially informative on its own. Water vapor is exciting, but it can exist on many worlds that are not habitable. A combination of gases out of equilibrium can be more suggestive, like oxygen and methane together. But even then, you have to rule out false positives. The universe is very good at making misleading atmospheres. So you learn to temper your imagination. You can let it wander, but not run. And in the quiet work of surveys, that is exactly what happens. A library grows. Not a library of books, a library of light curves, spectra, radial velocity time series, stellar parameters, and follow-up observations. Each planet is a card in a catalog with a name that sounds like a password and a few measured properties. Kepler 452b, TOI something something, HD numbers, GJ numbers. It is bureaucratic, and somehow that makes it more real, because mythology gives you names like Zeus. Science gives you file formats, and the file formats keep coming. You would think, with so many planets, the story would become less interesting. You would think it would blur into sameness, but it does not, because each new world is a small argument with your expectations. Some planets are on ultra-short period orbits, less than a day, skimming the stars so closely that their surfaces may be molten. Rock vapor atmospheres, sodium and silicon dioxide in gas form, the kind of weather report that makes you grateful for rain. Some planets orbit pulsars, dead stars spinning and flashing radio beams. The first confirmed exoplanets were actually around a pulsar in the early 1990s. Not exactly the cozy neighborhood you had in mind for life, unless life is feeling dramatic. Some planets orbit white dwarfs, stellar embers, tiny and dense. A planet transiting a white dwarf would create a huge dip because the star is so small. It is like an ant crossing a coin instead of a basketball. There are circumbinary planets orbiting two stars. Their transits are not periodic in the simple way because the stars move too. The geometry shifts. The dips come at irregular intervals. The data looks like a schedule written by someone who hates you. And yet, even that can be modeled because gravity is consistent about its cruelty. There are planets in systems with hot Neptunes that should not exist because close-in Neptunes seem to be rare. There is something called the hot Neptune desert, a region in parameter space where you do not find many such planets. The likely reason is that close-in Neptune mass planets lose their atmospheres, becoming smaller cores. So you get stripped cores, super-Earths that might be the skeletons of former mini-Neptunes. A planet's present state can be a fossil record of its past. Evaporation is not just a poetic idea. It is a measurable process. Some planets show helium absorption in transit, evidence of atmospheric escape. Hydrogen can be seen in Lyman alpha for some, though that is difficult due to interstellar absorption. A tail of gas can stretch behind a planet like a comet, pushed by stellar radiation and wind. If you could see it directly, it might look beautiful. It is also the slow death of an atmosphere. And if you want to feel this story in second person, you can by becoming the atmosphere itself. You are a hydrogen atom in the upper layers of a hot planet. Below you, deeper gas churns, heavier molecules sink, heat rises. Above you, the star is an enormous indifferent lamp blasting ultraviolet photons into your world. A photon hits you and kicks an electron into a higher energy state. Another collision knocks it free. Now you are ionized, and the stellar wind grabs you like a river current. You climb, not because you want to, but because your thermal speed is high enough. The planet's gravity is strong, but the heat keeps shoving. You reach the exobase, the region where collisions become rare. Above that, you are on your own. One more push, and you exceed escape velocity. Congratulations. You are no longer part of a planet. You are part of interplanetary space, an invisible exile, drifting until you join the star or the void. This is the kind of cosmic weather that never makes you feel nostalgic. And yet, these are the processes that shape the population of planets. Not just formation, but evolution. So when you hear astronomers talk about occurrence rates, about the radius valley, about the bimodal distribution of small planets, this is what it means. There is a gap in sizes between about 1.5 and 2 Earth radii roughly. Depending on the sample, many planets cluster below as rocky super-Earths. Many cluster above as sub-Neptunes with gas envelopes. The valley between them likely reflects atmospheric loss. Planets born with modest atmospheres either keep them and stay larger or lose them and shrink. A planet's size is not just what it was born with, it is what it managed to hang on to. Even in planet demographics, you can feel the theme. The universe gives you something. Then the universe tries to take it away. Now, since you are already thinking in catalogs, you can appreciate the calm logic of surveys. A survey does not chase one perfect planet. It counts what it finds and corrects for biases. Bias is not a moral flaw here. It is geometry and sensitivity. Transits favor short-period planets because you are more likely to see multiple transits in a given observation time. They also favor close-in planets because the probability of alignment is higher. Radial velocity favors massive planets in close orbits because the signal is stronger and repeats faster. Microlensing favors planets at moderate separations because that is where lensing sensitivity peaks. Direct imaging favors wide, young giants. So every method paints a different part of the elephant. And when you combine them, you begin to see the outline of a galaxy that produces planets as a byproduct of star formation. Protoplanetary disks are common around young stars. They are made of gas and dust, the leftovers of the collapse. Dust grains collide and stick, forming pebbles, then planetesimals, then embryos. Some grow large enough to accrete gas and become giants. This is not a neat process. It is a sticky, chaotic, collision-filled nursery. Planets can migrate through the disk. They can scatter each other. They can collide and merge. They can be ejected. The final system is what survives, not what was intended. Because there is no intention. And that is why 51 Pegasi b mattered so much. It was not just the first. It was the first that forced everyone to admit the process is messy. Now, you might wonder, in the gentle way you wonder in the dark, how did astronomers go from that first shocking hot Jupiter to this modern library? Partly it is technology, better detectors, better spectrographs, better stability, but partly it is also the social machinery of science. Teams learn to share data, to build catalogs, to standardize validation. The transit surveys created candidate lists, and the radial velocity teams prioritized follow-up. The community built archives. In exoplanets, an archive is like a city, a place where the data lives, where you can revisit old observations with new methods, because sometimes the signal was there all along, just below the noise. You reprocess old Kepler light curves and find new planets. You reanalyze radial velocity data with better models of stellar activity and separate planets from star spots. You combine data sets spanning decades. A planet that takes 10 years to orbit is not something you confirm quickly. You need patience, and you need a long baseline. This is where the quiet persistence of ground-based observatories still matters. Space missions are finite. They have fuel limits, reaction wheels that wear, budgets that end. Ground observatories can keep going, upgrading instruments, continuing time series. So while the space telescopes do the staring, the ground telescopes do the follow-up, the mass measurements, the confirmation. You might picture an astronomer at an observatory again, but now the scene is different. The dome opens, yes, but the instrument is more stable. The spectrograph might be in a temperature-controlled room, fed by optical fibers from the telescope. The light travels down the fiber like water through a pipe, isolated from flexure and vibration. Some spectrographs are kept in a vacuum chamber to avoid air pressure changes shifting the optics. Some are actively stabilized to milli-Kelvin temperature precision. It sounds extreme because it is. You are trying to measure a star's velocity change of less than 1 meter per second. That is a human walking pace. It is the speed of a casual stroll, measured from light years away through a column of atmosphere that is never still, using an instrument made of metal that wants to expand. So you do all of this just to reduce the lies to a manageable level. And once you do, you find smaller planets, super-Earths, sub-Neptunes, even Earth-mass planets around small stars. The holy grail for many is an Earth analog around a Sun analog, a small planet in a roughly 1-year orbit. That is harder because the transit probability is lower and the period is long. You need years of data to get 3 transits. You need exquisite noise control. Kepler found candidates like that, though many are faint and hard to confirm. The next generation of missions aims to do better with bright stars. Plato, a planned European mission, aims for long baseline photometry on bright stars. The Roman Space Telescope will do microlensing surveys and potentially coronagraph work. Ground-based extremely large telescopes will do high-resolution spectroscopy, possibly even detecting atmospheric molecules in Earth, like planets. by combining many transits. This is where the field is going. But you do not have to go there tonight in a rush. Stay with the calmer idea. There are machines watching while you sleep. They are counting shadows. They are measuring wobbles. They are building a quiet map of other systems. And in that map, the human story is less about conquest and more about restraint. Because the best exoplanet discoveries are not made by dramatic certainty. They are made by careful doubt. You see a dip, and you ask if it is a planet or a binary star. You see a wobble, and you ask if it is a planet or stellar activity. You see an atmospheric feature, and you ask if it is real or an instrument systematic. This repeated self-doubt is not weakness. It is how you keep from embarrassing yourself in public. Now, it is time to linger on a specific kind of quiet work. The way a survey mission actually turns a sky full of stars into a catalog full of planets. Imagine you are the mission pipeline. You receive raw pixel data. Not pretty images mostly, just numbers, counts, timestamps, detector temperatures, pointing information. Your first job is to extract light curves. That means defining an aperture around each star, summing the pixels, subtracting background, correcting for scattered light. It means dealing with crowded fields where multiple stars overlap and blend. Blending is a constant little betrayal. A planet transit in one star can be diluted by light from nearby stars, making the dip shallower. That means the planet's radius could be underestimated. Or a binary eclipse in a faint background star can appear as a shallow dip in a brighter foreground target. So you build models of the pixel response function. You use centroid shifts to see if the dip comes from a slightly different position on the detector. If the star's apparent centroid moves during the dip, that suggests the dimming source is not the target star. You also remove trends that affect many stars simultaneously. Kepler had reaction wheel issues, thermal cycling, pointing drift. TESS has scattered light from Earth and Moon, and orbit-related systematics. The pipelines use algorithms like co-trending basis vectors, human translation, common patterns that you subtract from individual light curves. Once the light curves are cleaned, you search. You run a box least squares algorithm, looking for periodic box-shaped dips. You scan periods, durations, phases. When you find a candidate, you model it. You fit the transit shape using limb darkening because stars are not uniformly bright disks. The edges are dimmer because you look through cooler layers at the limb. That limb darkening changes the transit profile. A transit is not a perfect box. It has rounded ingress and egress, a gentle curve. From the shape, you can estimate impact parameter, how centrally the planet crosses the star. A grazing transit looks different from a central one. You estimate the scaled semi-major axis related to the transit duration and the star's density. Yes, the star's density. In fact, a transit can tell you the star's mean density because of how duration and period relate. That becomes a cross-check with stellar models, so even a simple dip is packed with information if you trust your inputs. Then comes validation. You run tests to see if the dip depth changes between odd and even transits. If it does, you might be seeing a binary star with two different eclipse depths. You look for a secondary eclipse at phase half, which would suggest a stellar companion. You look for out-of-transit variability, ellipsoidal variations, beaming effects, reflection. A planet can cause some of these too, but the patterns differ. You look for signs of contamination. You check star catalogs, high-resolution images, Gaia data. Gaia, by the way, is its own quiet revolution. Gaia measures stellar positions and motions with ridiculous precision. It gives you parallaxes, distances, proper motions. It helps characterize host stars better, which improves planet radii. It can even detect astrometric wobbles from massive planets. Astrometry is the older cousin of radial velocity. Instead of measuring the star's velocity along your line of sight, you measure its position on the sky shifting. A star with a planet does a little dance. Radial velocity sees the in and out motion. Astrometry sees the side to side. Astrometry is hard because the shifts are tiny, but Gaia is patient and stable and space-based. It is building a massive catalog of stars, and within it, a hidden catalog of companions. So, the planet library grows from multiple directions. Now, with a validated transit planet, you often still want mass. So you schedule radial velocity follow-up. You point a precision spectrograph at the star and measure its wobble. For small planets, the wobble might be less than 1 meter per second. It might be buried in stellar jitter. Stellar jitter is the polite term for the star's own noisy behavior. Granulation, oscillations, spots, plages, faculae, a whole vocabulary of stellar surface structures. To mitigate this, you observe many times an average. You observe at specific timescales to average over oscillations. You model activity using Gaussian processes, statistical tools that can capture correlated noise. You also use activity indicators like the calcium H and K lines. You measure line bisectors, looking for asymmetries caused by spots. This is the part where exoplanet science becomes a partnership with stellar astrophysics. You cannot get rid of the star. It is the light source and the noise source. So you learn to speak star. Sometimes the star wins. You cannot get a good mass. Then you can only place upper limits. Or you use transit timing variations if the system has multiple transiting planets. Transit timing variations can yield masses without radial velocity. They require precise transit times and gravitational interaction. That is the beauty of multiple planet systems. The planets reveal each other, and this is also where you realize something almost poetic. The most useful planetary systems are often the most crowded because their interactions generate measurable effects. The mess becomes a signal. Now, once you have mass and radius, you can do population-level studies. You can plot mass versus radius. You can see clusters of rocky planets, gas-rich planets. You can see where photoevaporation sculpts the distribution. You can study how planet occurrence depends on stellar metallicity. Metallicity in astronomy means elements heavier than helium. It is a strange linguistic habit. Hydrogen and helium are the bulk of stars. Everything else is metal. Stars with higher metallicity seem more likely to host giant planets. That makes sense because you need solid material to build cores that can accrete gas. Small planets seem less sensitive to metallicity. They form readily, even around stars with lower metal content. So, giant planets are picky. Rocky planets are not. That is another quiet shift in perspective. It suggests that Earth-sized worlds could be common, even early in galactic history. But common does not mean habitable. And habitable does not mean inhabited. You can let those thoughts hover without resolving them. Now, since you are still in the mood of quiet machines, you can drift toward one of the most effective forms of exoplanet science, the long baseline survey that simply refuses to stop. Kepler's prime mission stared at one field for about 4 years. That length is not arbitrary. It was chosen so that an Earth analog with a 1-year period could transit at least 3 times. 3 transits is the typical threshold for a strong detection. 1 can be a fluke, 2 is suggestive, 3 is a pattern. So Kepler was built to be boring. It sat in an Earth-trailing orbit, keeping a stable thermal environment, minimizing interruptions. It was designed for high photometric precision, not sharp images. And that is another counterintuitive point. Kepler did not need pretty pictures. It needed consistent brightness measurements. Its pixels were large, so each star's light spread across fewer pixels, reducing read noise concerns. But that also increased blending. Every design choice has trade-offs. Then, after reaction wheel failures, Kepler became the K2 mission, pointing along the ecliptic and using solar pressure balancing. It was a graceful salvage, turning a crippled instrument into a productive survey. Again, not dramatic, just stubborn engineering. TESS, on the other hand, scans the sky in sectors, watching each for about 27 days, longer near the ecliptic poles. It focuses on bright nearby stars, giving you planets that are easier to follow up. So Kepler gave you statistics, TESS gives you targets, and the ground-based networks like WASP and HAT provided many hot Jupiters and other short-period planets, especially around brighter stars. This is how the modern exoplanet ecosystem works. Surveys find candidates. Follow-up confirms and measures mass. Space telescopes characterize atmospheres for select targets. Theoretical models interpret, and then are humbled by the next data release. Now, you may have noticed a pattern in this entire story. The first exoplanets found were the ones easiest to detect. Hot Jupiters in radial velocity, big short-period transiting planets. Then, as methods improved, smaller and longer-period planets joined. So, you might assume the most Earth-like planets are just around the corner, waiting for better tools. Yes, and also no, because Earth-like is not just a radius and an orbit. It is a composition, an atmosphere, a history, and a star that behaves. And the star, again, is often the deal breaker. Sun-like stars are relatively stable compared to many smaller stars, but they still have cycles. They have spots and flares. They have 11-year magnetic cycles like the Sun's. They have long-term variability that can mimic planets in radial velocity. So, finding an Earth analog around a Sun analog is like trying to hear a quiet metronome in a room with a humming refrigerator and occasional floor creaks. You can do it, but you need patience and careful modeling. There are candidates and detections approaching this regime. Proxima Centauri b, though around a red dwarf, is an example of a low-mass planet found via radial velocity. It is close, and it is tempting, and it is bathed in flare activity. There are other nearby systems, like those around Tau Ceti, with debated signals and long-term noise issues. This is where exoplanet science feels less like conquest and more like arguing with your own data for years. And that is actually the appropriate emotional tone. because if you want truth from a noisy universe, you should expect to work for it. Now let us take a slightly different angle, still within this quiet library. You have been thinking of planets as single objects, but a planet is often part of a dynamic system. Multiple planets can be inclined, meaning their orbital planes are tilted relative to each other. Our solar system is relatively flat, with planets within a few degrees. Many exoplanet systems are also flat, especially compact multi-planet systems. But some systems have misaligned planets, or even retrograde orbits. Hot Jupiters, in particular, sometimes have orbits that are tilted relative to the star's spin axis. This is measured through the Rossiter-McLaughlin effect during transit. The Rossiter-McLaughlin effect is a spectral distortion. A rotating star has one limb moving toward you and the other moving away, causing broadening of spectral lines. When a planet transits, it blocks part of the rotating surface, causing an apparent radial velocity anomaly. From that anomaly, you infer the projected spin orbit alignment. Human translation, you learn whether the planet's orbit matches the star's equator. Why does misalignment matter? Because it suggests a violent history. Migration through the disk tends to preserve alignment. High eccentricity migration through scattering or Kozai cycles can tilt orbits. Kozai cycles happen in three-body systems where a distant companion induces oscillations in inclination. A planet's orbit can become very elongated, bringing it close to the star at periastron. Tides then circularize it into a close orbit, so a hot Jupiter may have started far out, been perturbed into a crazy orbit, then tidally damped into a short period orbit, possibly misaligned. This is the kind of story you can read from a few spectral distortions. A planet is not just where it is how it got there. And in this, exoplanet science becomes like geology. You see the present state and infer the past. Now, you may want in the back of your mind to keep returning to the original anchor, 51 Pegasi b. It was a hot Jupiter. It was a surprise. It was the proof that planets around sun like stars can be found. But its deeper role was cultural. It taught astronomers to stop assuming. It taught them to let data lead, even when it is inconvenient. And in the decades after, the field became what it is now, a library, a census, a discipline of cautious inference. That library has its own quiet dramas. Sometimes a planet is announced and later retracted. Signals can be spurious. Activity can mimic planets. Data can be overfitted. The retractions are not scandals in the sleepy sense. They are normal. They are what happens when you push instruments to their limits. A classic example is the difficulty of detecting small planets around active stars. Signals appear at periods near the stellar rotation period or its harmonics. You think you found a planet, and then you realize you found a star spot pattern. So the community develops better tools, better statistics, better caution, validation frameworks like VESPA, and statistical false positive probability calculations, follow-up protocols, multicolor photometry checks. Again, boring is the point. Boring is what keeps you honest. Now, as the library grows, a natural question arises. How do you decide what to study in detail? You cannot characterize everything. Time on big telescopes is scarce. Space telescope time is scarcer. You have to choose, so you prioritize planets around bright stars because you get more photons and better spectra. You prioritize planets with large-scale heights, meaning low gravity and high temperature, because their atmospheric features are larger in transmission. Scale height is a physical idea that becomes a practical filter. A puffy atmosphere with low mean molecular weight, like hydrogen, has a large scale height. That means atmospheric absorption features are stronger, easier to detect. A heavy atmosphere with molecules like nitrogen or carbon dioxide has a smaller scale height. Features are muted, so ironically, the easiest atmospheres to detect are not necessarily the most Earth-like. Earth's atmosphere is thin relative to the planet's radius, and the signals would be tiny at interstellar distances. So the first era of atmospheric characterization focused on hot Jupiters, then warm Neptunes, then sub-Neptunes and super-Earths for the best targets. Now, with James Webb, you can see deeper and more precisely. You can detect molecules like water vapor, methane, carbon dioxide, carbon monoxide, and sometimes sulfur-bearing compounds. You can detect clouds indirectly by their flattening effect on spectra. You can infer metallicity of atmospheres and carbon-to-oxygen ratios, which relate to formation location. A planet that formed beyond certain ice lines may have different composition. Ice lines, or snow lines, are distances in the protoplanetary disk where specific volatiles condense. Water ice line, carbon dioxide ice line, carbon monoxide ice line. These lines matter because solid material accumulates differently beyond them. So a planet's atmospheric composition can preserve hints of where it formed, even if it migrated. Again, the theme returns. The planet moved, but chemistry remembers. Now you might ask, what about the first exoplanet around a sun-like star? Has its atmosphere been studied? 51 Pegasi b does not transit, so transmission spectroscopy is not available. But it has been detected with high-resolution spectroscopy in some studies, using cross-correlation methods to pick out molecular lines from the combined light. High-resolution spectroscopy can separate planet and star by their Doppler shifts because the planet moves quickly in its orbit. You take a high-resolution spectrum and search for faint molecular patterns that shift in velocity over time. It is like trying to hear a quiet instrument in an orchestra by knowing the melody and looking for it. This has been used to detect molecules and measure winds and rotation in some hot Jupiters. So even non-transiting planets can sometimes be characterized if you are stubborn enough and the planet is bright and infrared. This is a reminder that the methods are not rigid categories. They blend and evolve. Now, since you have been living in this library of planets, it is worth visiting the quietest thought in the room. What does it mean that planets are common? It means star formation naturally makes disks. It means disks naturally form planets. It means the galaxy is full of gravitationally bound leftovers. But it also means something about time. Many of these planets are older than Earth. Some are younger. Some orbit stars that will outlive the sun by orders of magnitude. Red dwarfs can burn for trillions of years. If life can arise around them and survive early flare phases, there could be a very long future for biology in the galaxy. Or not. The universe does not owe you that either. Still, the time scales are humbling. The human era of exoplanets is a few decades. We have gone from 0 confirmed planets around Sun-like stars to thousands of confirmed exoplanets and many thousands more candidates. That rate of discovery is fast by human standards and slow by cosmic ones. It is like noticing a few raindrops and trying to infer the shape of the storm. Now, stay in the mood of gentle inference, because there is another subtle effect of this library. It changes how you think about your own solar system. For a long time, Jupiter was treated as normal. Gas giants were assumed common, but Kepler suggests that hot Jupiters are actually rare, around about 1% of Sun-like stars. Cold Jupiters are more common, but still not universal. Our solar system lacks super-Earths and sub-Neptunes inside Mercury's orbit. Many systems have them, so our architecture is not the default. It is just one stable outcome. This matters because it feeds back into planet formation models. Why do some disks produce close-in super-Earths and others do not? Why do some produce hot Jupiters and others do not? What role do giant planets play in shaping inner systems? By migrating or blocking migration? There is a hypothesis called the Grand Tack, where Jupiter may have migrated inward, then back outward, shaping the distribution of material and perhaps explaining Mars's small mass. Whether it is true or not, the existence of many diverse systems makes such dynamical histories plausible. You stop thinking of planets as having fixed birthplaces. You start thinking of them as migrants, refugees, survivors of early chaos. This is not just poetic. It is a dynamical reality in simulations. Now, because this is sleep content, you do not need to hold all these details tightly. Let them drift like slow-moving clouds. But keep one thing anchored. All of this started with noticing tiny changes. A wobble, a dip, a pattern. The machines and surveys are extensions of that same idea. They are just more systematic, more relentless, less romantic. And as the surveys continue, the library becomes useful in a different way. It becomes a way to plan the next step. If you want to search for life, you need targets. If you want to understand planetary climates, you need a range of examples. If you want to test formation theories, you need demographics. So the survey catalogs are not just trophies. They are the base map. Now, imagine yourself gently as an entry in that catalog. You are a planet candidate, a possible dip in a light curve, flagged by software. You are labeled with a sterile identifier, something like TOI and a number. No poetry. Just a tag so humans can talk about you without confusion. You sit in a queue. Some candidates get promoted quickly because the signal is strong and the host star is bright. Some languish for years because follow-up is hard or ambiguous. Some are quietly declared false positives and archived. The universe does not care which you are. Humans do, because humans crave clean lists. So you get follow-up. A ground-based telescope observes your next predicted transit. If it sees the same dip, you gain credibility. If it sees nothing, you might be an artifact. A high-resolution imager checks your star for nearby companions. A radial velocity spectrograph measures your star's wobble. If the wobble is huge, you are not a planet. You are a star pretending to be small. If the wobble matches and the mass fits and the false positive probability drops, you become a confirmed planet. Congratulations, you are now a line in the exoplanet archive, and someone will use you in a plot. This is the real afterlife of worlds. To be a dot on a diagram, and as the archive grows, you can do something humans love. You can name patterns and pretend you understand them. The hot Jupiter pile up at 3-day periods, the sub-Neptune radius peak, the occurrence rate as a function of stellar type, the metallicity correlation for giants. You can model the planet mass function. You can infer typical system multiplicities. You can even compare to our own solar system's position. In these distributions, it is not central. It is one sample. Now, all of this quiet work is happening while the rest of the world sleeps. That is not metaphorical. Observatories run at night. Space telescopes run continuously. Data centers process while office lights are off. It is a strange industry of nocturnal measurement. And because you are listening to this in bed, it is worth keeping the contrast gentle. Outside, the real night sky is full of stars that look steady. Inside, in the archives, each of those stars is a potential system with its own gravitational music. The survey missions do not hear music, they hear numbers. But the numbers, when folded, reveal rhythm. Speaking of rhythm, you can return to the transit itself and appreciate how much information is hidden in a simple blink. When a planet transits, the ingress and egress times tell you about the planet's speed and the chord it cuts across the star. The duration tells you about the orbital distance relative to the star's size. The depth gives you radius ratio. If the transit depth varies over time, it could be star spots crossing, or it could be planetary rings, or it could be disintegrating debris. Rings, by the way, are not just for Saturn. In principle, exoplanets can have ring systems too. A ring system would produce a transit that is deeper and more complex. With asymmetries, there have been candidate ringed exoplanets suggested, though confirmation is difficult. A ringed planet can mimic a larger planet, complicating radius estimates. Moons, similarly, could exist. Exomoons are difficult to detect because their signals are small. They could produce extra dips or transit timing and duration variations. There have been candidates like Kepler 1625b, debated and not settled. The search for exomoons is like the search for quiet footsteps behind the footsteps. Possible, but hard. And then there are the more subtle photometric effects. A planet close to a star can reflect light, causing a phase curve invisible. The star can also be slightly beamed due to its motion, relativistic beaming, changing brightness. Ellipsoidal variations occur because the star is tidally distorted by a massive planet or companion. By modeling these, you can sometimes estimate the planet's albedo. You can infer whether it is reflective or dark. Many hot Jupiters seem to be quite dark, invisible, absorbing light with atmospheric alkali metals and haze. Some are brighter, with clouds reflecting. So even reflected light becomes a clue. Now, let us drift back toward the machines one more time, because the outline you are following has not finished living in that space. Space telescopes are not just watchers, they are also schedule-bound creatures. They have pointing constraints. They cannot look too close to the sun because they would overheat or blind sensors. They have momentum management because reaction wheels spin up and need unloading via thrusters. They have data downlink windows. They have limited onboard storage. So even in space, watching is not pure freedom. It is constrained patience. Kepler had to roll 90 degrees every quarter year to keep its solar panels illuminated and maintain thermal balance. That introduced systematics at each roll because stars fell on different pixels. TESS has an orbit around Earth in a resonance with the Moon, designed for stability and long observing windows, but it still has scattered light events and interruptions. James Webb sits at the Earth-Sun L2 point, a gravitational balance point, with a sun shield always facing the Sun and Earth. It keeps the telescope cold, allowing infrared sensitivity. Cold is crucial in infrared because any warm telescope emits infrared light, becoming its own noise source. So Webb is like a giant, delicate thermal management exercise with mirrors attached. And because Webb is so sensitive, it can detect small spectral features in exoplanet atmospheres. But it can also be fooled by stellar variability. M-dwarf stars have spots and flares. If you observe a transit while the star's brightness changes, your inferred spectrum can be contaminated. So, observers need to model the star's heterogeneity. Different spot coverage on the stellar disk can imprint wavelength-dependent signals that mimic atmospheric features. Again, the star is always part of the story. Now, if you want to feel the quiet grind of this, imagine yourself as a single photon. You leave the star's photosphere after a chaotic journey through plasma. You escape into space, traveling for years, for decades, for centuries depending on distance. You do not age. You do not get tired. You carry a wavelength, an energy, a piece of information. You pass through interstellar dust, perhaps scattering slightly. You pass through the heliosphere, the sun's magnetic bubble. You reach the telescope. You hit a mirror. Reflect, reflect again. You pass through a grating or prism if it is spectroscopy. You land on a detector and liberate an electron. The electron becomes a count. The count becomes part of a spectrum. The spectrum becomes part of a time series. The time series becomes part of a plot, and a tired human years later stares at that plot and decides you imply methane or water vapor or a planet mass. You did not intend any of that. You just traveled. It is almost insulting how much meaning humans can extract from indifferent light. Now, with all this in mind, the growing library can feel both satisfying and slightly absurd. Thousands of planets, and still the most common types are ones we do not have at home. Sub-Neptunes, super-Earths, worlds with sizes between Earth and Neptune. The question becomes, what are they like really? Are super-Earths just big rocky planets? Or are they mini Neptunes with thick atmospheres? The answer is sometimes one, sometimes the other. There may be a transition around about 1.5 Earth radii where planets above that tend to have volatile envelopes. But there are exceptions. The composition depends on mass, irradiation, formation history, and atmospheric loss. And for the ones that might be rocky and temperate, around small stars, you start to ask about surfaces. Could there be oceans? Could there be continents? Could there be atmospheres stable against stellar winds? This is where the soft detour of meaning returns. But you do not have to go too deep. You can just note that the library creates a new kind of humility. Your planet is not unique in having rocks. It might be unusual in having long-term stable surface water. It might be unusual in having a large moon. It might be unusual in having plate tectonics, or it might not. We do not know yet. Ignorance is part of the calm here. It means the story is not finished. It means the universe still has leverage over your certainty. Now, to keep the pacing gentle, let us stay on the practical side again. How do astronomers decide if a planet is in a habitable zone? They compute stellar luminosity, effective temperature, and then define a range of orbital distances where incident flux would allow surface liquid water for certain atmospheric assumptions. There are conservative habitable zones based on the runaway greenhouse inner edge and maximum greenhouse outer edge. There are optimistic zones based on empirical limits from Venus and Mars. But these are just flux-based zones. Real habitability depends on atmosphere, geology, magnetic fields, rotation, obliquity, and stellar behavior. A tidally locked planet around a red dwarf may have permanent day and night sides. That could cause atmospheric collapse on the night side unless winds redistribute heat. But models show that with sufficient atmosphere, heat can be transported. A planet around a flaring red dwarf may lose its atmosphere entirely unless it has a strong magnetic field or replenishment. So habitable zone is a starting point, not a conclusion. It is a place to aim your instruments, not a reason to assume. Now, since you are not concluding anything tonight, you can let the habitable zone remain what it is, a gentle suggestion. The more concrete thing is still measurement. You measure what you can: radius, mass, orbit, stellar type, insolation, sometimes atmosphere. Then you build the distribution and try to understand the processes shaping it. This is why the quiet work of surveys matters so much. It gives you enough samples to make statistical claims. For example, you can estimate eta Earth, the occurrence rate of Earth-sized planets in habitable zones around Sun, like stars. The value is still uncertain because definitions vary and detection completeness matters. But it is not zero. It appears to be some non-trivial fraction. That alone is enough to change the philosophical landscape, even if you never find life, because it means Earth-sized temperate worlds might be common enough to be worth searching. Now, let us make that search feel tactile again, because you are still the second person here. You are a data analyst in the quiet hours. Your screen glows in a dark room. You scroll through light curves, each one a tiny heartbeat of a star. Most are flat, some show noise, some show dips. You click a candidate and fold the light curve on the detected period. The dips line up. A neat little notch appears. It is satisfying in the way only pattern recognition can be. Then you check the diagnostics. Odd, even transit depths, consistent. Secondary eclipse, none detected. Centroid shifts, none significant. You mark it as a planet candidate worth follow-up. This is how the library grows, not in epiphanies, but in small approvals. Then you send it to follow-up teams. They schedule observations. A radial velocity team measures the wobble, but the star is active, showing rotational modulation. They observe many times, spread out. They model the activity as a quasi-periodic signal. They look for the planet's period in the residuals. Sometimes it appears cleanly, sometimes it does not. If it does, you get mass and confirm. If it does not, You may have a planet with unknown mass, or you may have no planet. It is all very calm and all very unforgiving. Now, the library is not just a list, it becomes a training ground for new methods, machine learning classifiers to triage candidates, better detrending algorithms, joint modeling of transits and radial velocity, community validation, where multiple groups check the same candidate. Exoplanets are now a mature field, and maturity looks like process. Now, to keep the narrative drifting forward, it is time to let the library become a landscape. Imagine the Milky Way as a disk of stars, between 200 billion and 400 billion stars, depending on estimates. If planets are more common than stars, then there are at least hundreds of billions of planets. Many are small. Many are in systems unlike ours. Many are in orbits we have not detected yet, because long periods take long time. There are Jupiter analogs out there, orbiting at 5 AU light distances. They take years to complete an orbit. We are only now getting the time baselines and precision to detect them routinely. There are Saturn analogs, Neptune analogs. There are planets in outer systems that are cold and quiet. Microlensing has hinted at populations of cold planets. Radial velocity surveys over decades are now detecting long-period companions. So, the library is still biased toward inner planets, but it is slowly reaching outward. And as it reaches outward, it will start to answer a question about our own story. How common are solar systems that look like ours? Not identical, but with inner rocky planets and outer giants on roughly circular orbits. We do not know yet. But the fact we are asking is itself new. Before 1995, you could not ask that question with data. Now you can, slowly. Now, in the middle of this, there is still another quiet kind of survey, not transits, not radial velocity, but surveys of young stars and disks. Astronomers observe protoplanetary disks with telescopes like ALMA, the Atacama Large Millimeter Array. They see rings and gaps in dust. Those gaps may be carved by forming planets. You are watching planet formation in progress. In a way, the images are eerie, concentric rings like tree growth, but made of dust and ice, structures shaped by gravity and pressure. It is not a finished system. It is a system in the act of becoming. So the library of exoplanets connects to a library of disks. You start to tie populations to birth environments, disk mass, metallicity, lifetime. Disks do not last long in cosmic terms. A few million years, then the gas disperses. Planet formation, at least for gas giants, must happen before gas is gone. So timing matters. If a planet does not form quickly enough, it becomes a different kind of planet. Again, the universe is not poetic, but the outcomes feel like they were plotted. Now, as you continue drifting through this topic, there is a gentle human question embedded in the background. If there are so many planets, why do we not see them with our eyes? Because they do not shine much. Because they are drowned by starlight. Because they are far. But the methods we use are clever ways to avoid that problem. We let the star betray the planet by wobbling. We let the star betray the planet by dimming. We let gravity betray mass through lensing. And that is an oddly consistent theme. Planets are discovered through the things they cannot help doing, pulling, blocking, bending. They are found by their effects, which is a very scientific way to live if you think about it. You too are mostly known by your effects, your footsteps, your voice, the warmth you leave on a chair, the way you change a room's air. You do not have to be seen to be real. Now, that thought can sit quietly in your mind as the library continues to fill. And from that library, you can move gently into the next part of the story, because once you have enough worlds, you start caring less about the first detection and more about the strange, careful art of guessing what a world is like without ever seeing its surface. You are still not looking at pictures. You are not landing probes. You are not tasting the soil. You are, as always, listening to small changes in light and trying to build a reality from them. And that is where the story naturally wants to go next, into the calm, limited, strangely powerful